Right, it's exactly 10 a.m. PST. Hello, everyone. This is Pranab Ghosh. I'm in India right now. So, can everyone hear me? So, so this is the first session of a 8-part webinar on anomaly detection. So the focus of this webinar is on practical application of various anomaly detection algorithms in real life and how to deploy the anomaly detection models. And essentially, that's the focus, practical applications. As far as the algorithms go, I'll kind of describe them at a high level, at an intuitive level, without going into a lot of details, but I'll provide all the references in case anyone interested. They can always, go into more details, but I won't be covering a lot of details of the various algorithms. So what exactly do we mean by anomaly detections? Essentially, unfortunately, it's an area of machine learning which doesn't get the attention that it deserves, but it's something that comes up all the time in real life, based on my experience. So the idea is that you have some data stream, and whenever anything unusual happens, and I'll get to this a little bit later as far as what unusual or abnormal means, you want to get notified, because that may indicate something seriously going wrong. So you want to be notified so that you can kind of troubleshoot into it and find out what the potential problems are and essentially deal with it. So it's essentially an operational problem. Whenever you have large volumes of operational data, and no matter what the domain is, that's where it's applicable. So it's kind of it's basically an operational issue. So for anomaly detection, prior to machine learning, what people used to do is they used to define, the domain experts, they used to define rules as far as what exactly is anomaly. These are all static rules. So, and that's not very robust, because especially in an environment which is dynamic, and the data may not even be stationary. Things could be changing, or you may have a very large volume of data. So it's a solution that's not very robust, and it's not very scalable. So with machine learning, it's a very different approach, and the approach is using machine learning to find patterns in normal data. So it's almost like any other area of machine learning, just like supervised learning or unsupervised learning. You build a model for using normal data. So whenever you come across any data that deviates from that model, that's an anomaly. Now, what is the model? So that depends on the algorithm. So for example, if it's a simple, let's say you have Gaussian data, and if it's and you're doing some anomaly detection based on z-score, then your model is basically the Gaussian distribution, empirical Gaussian distribution. So it depends on the model. Now, in anomaly detection also, there can be supervised learning and unsupervised learning. Supervised learning generally doesn't work very well, because first of all, you have to label the data, and then anomalies are pretty rare. So even if you take the supervised approach, you'll be dealing with this extremely unbalanced data. So it doesn't work very well, and it's not used. So most of the algorithms that people use, they're all unsupervised. So our focus will be on unsupervised algorithms. If you are interested more about this anomaly detection algorithm, here's a link. It's a survey of various anomaly detection algorithms. I think the paper is about 10 years old, but it's still really good. If you're interested, you can read that. So these are the 8 sessions in the webinar that we'll be covering. So the first one is the exploratory data analysis. That's the topic for today. The next 4 are the core of the webinar, which are going through different kinds of anomaly detection depending upon what kind of data you find in the first phase, which is the EDA or the exploratory data analysis. And then number 6, 7, 8, they are kind of special topics. For example, 6 deals with non-stationarity of the data. So for example, you build a model and then there is a drift. You have to detect the drift and maybe you have to rebuild that model. So which is a typical machine learning deployment problem. So we have the same issue here in anomaly detection also. Anomaly aggregation, that's kind of interesting. It's more of a practical issue. Now, I think the best way to explain that is through an example. Let's say you're a large e-commerce retailer and you're tracking your hourly sales or or daily sales. And so you have, so if you look at your data, maybe you have a hierarchy in the data. Maybe you have, the product sales data, and then you may have different product categories or different departments. So what this allows you to do, and you're tracking anomaly at the lowest levels. So think of it like a tree or with a hierarchical structure, where at the leaf nodes you have the actual product sales data. So, and that's what you're tracking with your anomaly detection model. So when you detect an anomaly, so this aggregation essentially allows you to percolate that anomaly up the hierarchy. So imagine you're building a dashboard. So in the dashboard, you can show the health of your sales data at various levels. Maybe at the department level or category level, or even at the whole enterprise level. So it's a way to aggregate the anomaly scores. To it's an aggregation logic essentially. Anomaly threshold, the last one is kind of interesting. One of the really thorny issue with anomaly detection, most of the algorithms, you get a score. And typically, higher the score, more anomalous the data is. So what happens in reality, you can always display the score if you have a dashboard, but in reality, what happens is a lot of customers, they want some sort of a binary decision, is it anomalous or not? So that means you have to take that score and then you have to apply threshold, and then, if it's above the threshold, it's anomalous, otherwise it's not. And deciding what the threshold is, it's extremely tricky. You can never get it right. So what I'll be doing, as we'll go over it in a different session, is once you get the anomaly score, we'll just do some statistical, hypothesis testing, and based on that, we'll decide, whether it's anomalous or not. Even then, it may not make people happy because, if you're doing statistical tests, you'll be looking at p-value and some alpha and all that. But, again, you have to decide what the alpha is. So even then, it may not be perfect. So what can happen is, once you have, let's say you have some threshold and you have labeled your data as either as anomalous or not, then if you have a dashboard and you have some administrator, and if the administrator decides whether it's truly anomalous or not, then you can mark your data as, whether it's false positive or false negative. Let's say your algorithm thought it's anomalous and the admin doesn't think so. So that's a false positive, right? So you can take all that feedback and run that through another machine learning algorithm to kind of tune your threshold. So that's kind of a special topic. These are some use cases from various domains. So, the use cases are essentially endless. Anytime, any domain you're dealing with in a large volume, operational data, this issue comes up. But here are some use cases just to give you some idea. And I have broken them up into, different domains or categories. So the first one is IT ops, that's some typical data stream you might find in an IT shop. Then e-commerce, something from banking, then human resource, healthcare, industrial, security. Anomaly detection is huge in security. You cannot do any kind of, you cannot build any system for cybersecurity without some sort of anomaly detection somewhere. It's just a very essential part of any cybersecurity solution. Then telco, then ticketing system. This is another kind of IT operation. The target audience essentially are mostly, but may not exactly be the case all the time. People who are dealing with operational data, CO, CIO, and DevOps, and even software engineers. So session 1 is the exploratory data analysis, and we'll be using Python for that. And so why do we need to do this? Now, if you look at if you do any research on anomaly detection algorithm, what you'll find is there are hundreds of different algorithms. It's just endless. So how do you navigate through all that? So one way to do that is to do some EDA on your data and see what kind of data you have. And then based on that, you choose, then once you have figured out what kind of data you have, then for that type of data, you may have a choice of algorithm, but at least you have been able to narrow down your choices a little bit. So it helps to do some EDA before you choose an algorithm and get going. So that's what you expect to learn from today's session. Why the EDA is necessary, and then once you have done the EDA, how do you choose the appropriate anomaly detection algorithm? So there are even some, I don't think there is any unanimous opinion as far as what is anomalous data. I mean, it depends really on the use case and the domain. For example, for some people, any kind of extreme value is anomalous. For some, any rare value is anomalous. So it depends on the application. Now, any data whose distribution has some sort of a central tendency, or the mass is kind of has a central located around the central region, typically extreme values will tend to be rare, right? But it depends on the distribution. But if you have a bimodal distribution, then that's not the case. If your data is autoregressive, in the sense that if it's highly correlated with past values, then your data is anomalous based on what were the data values in the recent past. So in that case, whether the data is anomalous or not will depend upon its history. So there are various ways to look at the data and define what is an anomaly. So it really depends on your data and your use case and the context. There is nothing, one size fits all kind of anomaly definition. It really depends on your data. So now we have to do some slicing and dicing of the data. So first, there are two different ways to look at the data, depending on the dimension of the data. Is it univariate or is it multivariate? So univariate is, for example, if you're looking at CPU usage in a server, that's univariate. Multivariate is when you have, multiple data sets and they're highly correlated with each other. So one example might be, you may have a bunch of sensors on some piece of machinery, and those sensor data, they might be correlated with each other. It's very likely. So that's one way of looking at the data. So another dimension is whether the data is autoregressive or not. So if it's not autoregressive, I'm calling it independent. So autoregressive means it's correlated with its past data. And one way to find out whether it's autoregressive or not is to do autocorrelation, and we'll be looking at that. So for example, some health monitoring data will be autoregressive. For example, ECG data, there are some definite patterns. So the value you see now, will be highly correlated with the past values. So if you combine kind of these two ways of looking at data, there are like 4 different scenarios or 4 different categories as far as data is concerned. One is scalar independent, then the scalar sequential. By sequential, I mean autoregressive. It's correlated with past value. Then vector independent, that means multivariate, but not autoregressive. And then the last one, which is most complex, it's multivariate as well as autoregressive. That means I'm calling that vector sequential. That means it will have significant cross correlation as well as within a particular data stream, a significant autocorrelation. So what I'll do next is go through a Python notebook and run some code to analyze some data to find out which of these 4 categories my data belongs to. Because as I was saying, that's the first step. Without that information, you cannot, it's just literally impossible to navigate through all this, myriad of anomaly detection algorithms that's out there. So it helps to, navigate through all the algorithms and then, decide on what algorithms to use. So for this EDA, I'll be using a Python class that's in my GitHub repo. And so this Python class, essentially it's built on top of a lot of existing Python libraries like NumPy, Panda, SciPy, StatsModel, sklearn. The reason I did this is because it becomes really easy to do EDA, because when they're all in one place, you don't have to worry about numerous imports. Everything is wrapped in one Python class, and it's got a nice, clean, user-friendly interface. It becomes a lot easier to use. So that's the reason I wrote this, because this is something. This is a pain I felt myself. So when I was doing EDA with data, so I decided to write this tool just to make it convenient. So I haven't implemented any algorithm. They're simply, all the class methods are simply wrappers around existing, Python, various Python math and statistics libraries. So I can quickly show you. So here is a blog post on this tool. So if you scroll down, so it gives you all the salient features of this tool. So essentially, you can register multiple data sets. So you can think of a data set as like a NumPy array. So each data set, you can give it a name, and you can register your data sets from a file, from a Python data frame, or even a Python list. So once the data sets are registered, you can refer to them by their name and perform various operations. And the operations could be unary or binary. So for example, if you're just going to do autocorrelation of some data stream, that's a unary operation, right? But if you're doing cross correlation, that's a binary operation. And the result is always returned as a Python dictionary. And then also using Python pickle, you can checkpoint your whole workspace. It'll save all the internal state, all the data that you have loaded, so you can restart that anytime and continue with your EDA. So I find it really convenient and handy. I don't have to go and hunt around all the different Python libraries, read their docs, and do the imports. It's all wrapped in one Python class. So I'll show you quickly. So this is a Python class that does all that. It's got about 1,000 lines of code. So the first few are about loading the data, and then after that, various EDA functions. There are about 70 different functions right now. Anyway, so next I'm going to jump into the IPython. So as I was saying, we discussed about all these 4 categories of data. So the goal of this IPython notebook is to run some code so that you can explore the data and figure out what category the data belongs to. There will be some corner cases. There will be some data which will be kind of unique, doesn't fall into any of the special categories. We'll be talking about that also. For example, you may have spiky data, like data that's constant most of the time except for some spike, and the spike interval may not be may not even be constant. It could vary. I mean, the interval, it may have a narrow distribution, but it may not be fixed. So for something like that, I mean, none of these patterns will work. So you have to come up with some special algorithms to deal with it. I'll talk about that also. So by the way, everything, all the code I'm running here is in a GitHub repository called Avenir. So let me show you that quickly. So you can actually run this IPython notebook if you check out the repo, and there are some instructions on how to do it. This is essentially the environment I'm using as far as Python goes. I'm using Python 3.8. This is what you have to do if you want to run it yourself. These are the steps. So you have to check out the directory, and then you have to copy a bunch of files to a directory called python/nbook. Then you have to copy a bunch of properties file. By the way, my Python code uses a lot of it's heavily configuration driven, and all the configurations are defined in properties file, just like in Java. So you have to copy all the configuration files into the nbook directory. Then you can start your IPython notebook from the directory, and then once you have done that, you're ready to go. So our first task is we have some data we want to find out if it's got a Gaussian distribution or not. Okay. So this data happens to be temperature sensor data from a building. So the temperature kind of hovers around, let's say 70 most of the time, except that there is some random Gaussian noise around that. And so the idea is that if it deviates too much from that 70, that's an outlier. So in this case, you can use, anyway, let me come to that later. Anyway, so this is how you generate the data. So all the data is synthetically generated. I have another Python file called tsgen.py. So I'll be using that for generating all the data with various kinds of patterns. So in this particular case, it's going to generate some data with Gaussian distribution with mean at 70 and with a small standard deviation. And you can see 2 properties file here. So the properties files, so the first one is the default, and then the second properties file, you can override the defaults. And then I'm saving the data in this file. And this is a Python code to run that Data Explorer Python class that we just looked at. So you create an instance of the class, that's your object, and then you add data. So in this case, we are adding data from file numeric data. So And this is the name of the file, and then one means this is my column. So I'm interested in the second column in the data, and then I'm giving that column a name. So, and then once I have done that, you can see I can refer to the data using that name. So here I'm doing a plot, I'm doing an histogram, and then I'm doing an autocorrelation. So this is a plot. This is a histogram, which looks very close to a Gaussian distribution. Autocorrelation, we see a big spike at 0, which is expected because it's random data with Gaussian distribution. So it's supposed to have only spike at 0 and nothing significant. So you see that band there. So that band is essentially tells you whether any significant spike or not at other lags. So these are the different lag values on the x-axis. So this gives us some idea of the data. So we see that it's got Gaussian distributions and all that. But to be able to have a more stricter test on whether the data is Gaussian. I mean, visually it looks like Gaussian, but just to make absolutely sure, there are various statistical tests for Gaussian distribution. So here I'm using something called normal distribution. It's called Shapiro-Wilkes test. And you see the test result here. See the p-value is 0.561. So that means, and the significance level is 0.05. So that means the null hypothesis is that the data has Gaussian distribution. So we cannot reject the null hypothesis. So that means the data has Gaussian distribution. Now, if the data has Gaussian distribution, then it's going to be a lot easier for you to select what algorithm you should use. So if your data has Gaussian distribution, then you can pretty much, it's almost a no-brainer that you will be using an algorithm called z-score. Z-score is, I think most people know about that. It's how many multiple of standard deviation the data is from the mean. So then you have to apply a threshold on that. So in that case, in this case, you might set the threshold at, let's say, 3. So any data point that's more than 3 multiples of the standard deviation away from the mean will be an outlier in that case. Now, what if you have random data that doesn't have Gaussian distribution? So that's the next use case. So here again, we are doing plot, then we are plotting histograms. In this case, histogram is nowhere close to Gaussian. In fact, it's bimodal. It's got 2 modes. Autocorrelation is still, peak at 0 lag because it's still random data. And we know that random data has only, doesn't have any other significant peak except for, a lag, except for at lag 0. So we know that, it's not, so we can run a normalcy test here. So just for the, just to try something different, I used a different normalcy test. So let's see, look at the test results. It says, you see the p-value is close to 0 almost. So that means we have to reject the null hypothesis, which is the data is Gaussian. So that means the data is not Gaussian. So if the data is not Gaussian, we cannot use the same algorithm we used in the previous case. So you have to go looking for something else. So in this case, you have many choices. So for example, one algorithm is called robust z-score. So it's similar to z-score, except that it uses something called absolute. It's based on median. So instead of mean, it uses median. Instead of standard deviation, it uses something called absolute median deviation. So it's a deviation from median. And so the algorithm is based on that. And this algorithm doesn't require the data to have Gaussian distribution. So that's one option. Or you can use the some algorithms based on empirical distributions, for example, based on quantile values. Or you can use there are algorithms based on cumulative distribution. You can use that too. So you have a number of choices, and in real life, you just have to try them out and see, what's best. There is no way to really tell. You just have to, play around with it. So far, the data that we looked at, they were not autoregressive in the sense that the data was not correlated with its past value. As we saw from the autocorrelation, right? We didn't have any significant lag at any other lag value except for 0. So that means the data was not auto-regressive. So in this case, the data happens to be autoregressive, and this is the data that's for, it happens to be for blood pressure. So this is how you generate the data. Again, use the same Python class and use the configurations defined in the properties file, and then generate the data. Again, we do a plot, we do a histogram. So I'm doing a normalcy test. It happens to have a Gaussian distribution also. Next, let's do, so in this case, so next we'll be doing autocorrelation. Now, along with autocorrelation, we'll also be doing something called partial autocorrelation. So this is autocorrelation, and if you look at the autocorrelation, we are finding significant lags at lag 1, lag 2, 3, at least 3 more significant autocorrelation peaks, which tells us the data is autoregressive. Now, what is partial autocorrelation? So what partial autocorrelation does is that, let's say you're looking at autocorrelation at lag 5. So you have some data point and then another data point which is in the past, like 5 data points away. So what happens in a regular autocorrelation, that all the intermediate data points will also will be correlated with the data point you're looking at, between the current data point and the 5th one in the past. So what partial autocorrelation does is that it removes all the influence of the intermediate, data points. So that means when I'm looking at a correlation value at lag 5, it's really is the correlation at lag 5. There is no other influence from any other data points at different lags. And this is something that gets used, for example, if you do time series forecasting, that there's something called P. So that P is decided by how many peaks you have in the partial autocorrelation. So what anomaly detection algorithm to use in this case? Obviously, we cannot use any of those from the last 2 cases, because when the data is autoregressive, whether something is anomalous or not will depend upon its most recent history. It's not so much its absolute magnitude or its probability. It's what is the data value with respect to the past n data points. That's what is going to decide whether the current data point is anomalous or not. So again, there are various algorithms. One simple one is you can use any kind of time series forecasting algorithm. And then if your actual data point, let's say you use the past n data points to forecast the next data point. Now, if the actual value is too far away from the forecasted value, in other words, if the error is too high, that's likely to be anomalous. So this is one approach which is based on forecasting algorithms. So in this case, you can use for forecasting, you can use ARIMA or seasonal ARIMA, or you can use deep learning, like LSTM. You can also use, there are some simpler algorithms also. For example, you can use Markov chain, which is based on conditional probability and all that. So which basically tells you that you have a small window. Let's say you have a window of 3 data points. You find the joint conditional probability of making the 2 transitions within that window. And then if that probability is too low, then it's likely to be that small sequence is likely to be anomalous. Now, to be able to do that, you have to discretize the data. If you have real data, you have to discretize it, because Markov chain deals with states. So that's why you have to discretize the data. There are many other algorithms. These are just 2 examples I gave. Now, if you look at a lot of business data, they typically have a cycle and a trend. They have a seasonal cycle. Like they may have a day cycle. That means for every hour, there is a 24-hour cycle in the data. Or it could be a weekly cycle. That means there is a 7-day cycle in the data. Now, when the data has cycle and trend, it's also although implicitly, but it's also autoregressive, because a data point will be highly correlated with past data points. So for example, let's say you have a day cycle, then let's say you're looking at some sales data, then there's the amount of sales between, let's say 10 a.m. and 11 a.m. today will be highly correlated with amount of sales in the same hour in the previous day and the day before, right? So you'll find very strong autocorrelation. So the data is regressive, but it's a kind of a special kind of regression. I mean, autoregress, a special kind of autoregression. The autoregression is happening because of seasonal cycle in the data, as compared to autoregressive like in a generic sense. So in this case, also we are doing some plots. So in the plots, you can see clearly, there is a cycle, there is some noise. So typical business data will have some trend, some cycle, and then some random, Gaussian noise. And we see all 3 of those in the plot. This is a histogram. Then again, we are going to do autocorrelation. And if you look at the autocorrelation, you will find strong peaks. And the cycle in the autocorrelation corresponds to the cycle in your data. So this data is has a day cycle. That means period is 24 hours, which is why you'll see a cycle in the autocorrelation also. And there are peaks for every hour, because data for every hour is correlated with data that's 24 hours into the past, right? Partial autocorrelation also, you'll find you won't find so many peaks because of the because partial autocorrelation removes the influence of a lot of intermediate lags, but you will see a very significant peak at 24. And also at 1, I think this large peak at 1 is due to the trend in the data, because the data has a linear trend also. Next thing we are going to do, just to learn a little bit more about the data, the stats model has some libraries which will, given this kind of data with trend and seasonal cycle, it will break them up into different components. So here is the actual data. The second plot is the trend. It's not really perfect, because the trend, we used a linear trend when we generated the data. This is the seasonal cycle, and this is the remaining component. So you can tell the remaining component is a random Gaussian with a zero mean. So the actual data is essentially just the aggregation of these three components. So this library decomposes the data into these three components, so which helps you to visualize the data and learn about the data more. So for this kind of data, there are some, you can use the same algorithms as, for example, we use for just any kind of data that's not autoregressive, like the first two cases. The only caveat is that what you have to do is, instead of building one model, you have to build multiple, models. So for example, if you have a daily cycle and you have hourly data, you have to build 24 models. So one for each hour of the day. And then when you make predictions, you have to, depending upon which hour your data falls into, you have to choose the right model. So that's one way of dealing with seasonal cycles for anomaly detection. Another approach is to just to do this decomposition of the seasonal of your data. Take the residue, which is zero mean Gaussian, and then just do z-score on that. So if you see a large, if you find something anomalous based on the residue, which has zero mean, which is a zero mean, Gaussian data, then your, data has some outliers. So that's another approach. But that will depend upon how accurately this, this decomposition took place, right? So again, there are, various approaches. So what we have talked about so far, they're all for univariate data. Now within the univariate, again, there are two like subcategories. One is independent data, which doesn't have any kind of autoregressive property, and then autoregressive. Next, we'll be talking about multivariate data. So data that are highly cross-correlated with each other. So here I have an example of sensor data from 4 different sensors from a piece of machinery. These are like motion sensors. And in this case, the way the data was prepared was that no, actually there are 5 sets of data. The fifth data set will not be correlated with any of the rest, but the first 4 will be highly correlated with each other. So what I'm doing here in this case is that I'm calculating something called Pearson correlation. So basically it's a cross correlation. So what I'm doing here is I'm taking each pair of data sets and I'm finding the cross correlation. So for example, here is find, probably correlated, probably correlated, probably uncorrelated. So this is between data set 1 and 4. And as I said, 4 is not correlated with the rest. So any correlation of 4 with any of the other data sets, it will tell you, the test will tell you that it's not correlated. So once you have done that, so what you have discovered, going through this process is the first 4 data sets are highly correlated with each other. That means you have to treat the first 4 data sets as a multivariate data set and use multivariate anomaly detection algorithm. Whereas for the 5th one, you can use any univariate algorithm. Like 5th one is all the cases that we have discussed so far. So this is what you have to do. So for multivariate anomaly detection, again, there are various algorithms. There is something called local outlier factor, which is essentially like if you know about KNN clustering, K nearest neighbor clustering. So it's based on similar ideas. So intuitively, any data point that lives in a, so if you're looking at a multi-dimensional space, any data point that's in a space where the density is very low, that means it doesn't have too many other neighboring data points, that's a potential outlier. So that's the idea behind this algorithm. Isolation forest is another interesting algorithm. So the idea is that it's kind of like indexing. So if you, so it builds indexes on each variable, and then it tries to find the data, going through the indexes. And the data points that are kind of clustered together, you have to go through too many indexes before you can find the data. But for outliers, you don't need a lot of indexes because they are in a sparse region of your multidimensional space. Again, these are two example algorithms. They're popular, but there are others. So for example, one algorithm might be, you can use, if you use deep learning, you can use autoencoder. So autoencoder essentially has an encoder and the decoder, right? So it extracts the some latent vector from the data, lower dimensional latent vector. So what happens with anomalous data is that the regeneration error will be very high. So that means it's not fitting the encoded vector pattern. So if your regeneration error is very high, you know that the data is anomalous. So that's one way of using deep learning for multivariate anomaly detection. And the last one is it's cross-correlated as well as autocorrelated. So the data is highly correlated amongst themselves, but also correlated with itself. So it's got both. There are algorithms where in some cases you might be able to use some existing algorithms. For example, you might be able to use Markov chain where your state will be multi-dimensional instead of single dimensional. But it's the same algorithm that we have seen being used earlier. Or you can use algorithms specifically for this kind of data. So for example, you can do vector-based time series forecasting methods. We talked about scalar time series forecasting. So same approach, except that it's a vector. And then again, the idea is if your prediction error is very high, it's likely to be an outlier. And lastly, there are some special cases. And I'm just giving you an example. There may be many special cases. And what you will find that in spite of going through all this EDA and trying to figure out these are some common patterns, what the underlying pattern in the data is, so that that helps you to choose the right algorithms. You'll still find in real life, there are some patterns which doesn't fall into any of these categories. So for example, you may have data that's flat most of the time, and then there are spikes, and the spike interval may not even be fixed. It may have a very narrow distribution, but it may not be fixed. And for something like this, in any of the algorithms for all these different categories that we discussed about so far, none of that will work. Here to come up with unique solutions for this kind of unique pattern. So one approach for this might be to do some feature engineering and turn this univariate data into multivariate data, where one variable is the gap with the previous spike, and the second variable is the magnitude of the spike. So it's basically a bivariate data. So once you have the bivariate data, then you can use any kind of multivariate anomaly detection algorithm that we discussed so far. So for all these special cases, you have to come up with unique solutions, doing some extra work. Like here, we have to do some feature engineering to come up with appropriate solutions. So that's the end of my session, and so I'm open for QA. We probably have about 10 minutes left. Hello?
Yes, Pranab. There is some link from in the chat box. If you can pick it up.
Let me get to the chat box. Okay. Q&A, is that the one? Q&A?
Yeah, Q&A and also the chat box.
Okay.
Okay, I just read out some questions. Can we get the notebook afterwards is one. And also, what is the link for the repo is another question.
Yeah, so all the links are in the Google Doc. So we can share the Google Doc. So anyone interested, I'll provide the link for the Google Doc, so they can view the Google Doc. And all the links are within the Google Doc. And the links will be for the GitHub repo, the blog post, and basically these two, and some another paper I was referring to, which is a anomaly detection survey paper. Yeah.
Okay, another question is, can you please share the GitHub link?
Yeah, that will be in the Google Doc also.
Okay.
All the links will be in the Google Doc. Yeah.
Okay. Another question from William. What do you recommend to get the most from the course?
As I said, the focus is on practical application of machine learning based anomaly detection algorithms. So that's what you'll be getting out of this series of webinars for real life applications.
Yeah, sorry. So the next question is, can we implement an anomaly detection to access logs? Example on Apache web server.
Yeah, absolutely. So it depends. I mean, if you're dealing with numeric data, yes. But if it has text, that's a different story. I mean, I haven't covered, anomaly for NLP or anything like that. So that's a whole different problem. Okay, next.
Yeah, the common question that's coming through is, will there be a Google Doc which will be shared? Yes, definitely we will share the Google Doc, and also the recording of the session will follow.
Okay. The next one is there an autoencoder approach that can be used for anomaly detection? Yes, I did mention that when I was covering multivariate anomaly detection. You can definitely use autoencoder using either TensorFlow or PyTorch. But again, you'll be running into the same issue, which is common across all anomaly detection algorithms. You'll get an anomaly score, which in this case will be the regeneration error, and then you have to turn that into a anomaly level using some sort of thresholding. Yeah, you absolutely can use. GitHub link, please. And will this video be, yes. Will this video be on the YouTube, Sharon? I don't know anything about that.
Yes,
there is no video, it's all audio.
Yes, we will share it on the YouTube.
Okay.
Yes.
Okay. Yeah, we'll share the Google Doc. Multivariate anomaly detection over time dimension. One thing you can do is multivariate anomaly detection. You can go to scikit-learn, and it has two algorithms. One is called local outlier factor. One is called isolation forest. In fact, those two algorithms are also in the data exploration class, all wrapped up in a nice Python method. You can use that, or you can use sklearn directly. All my anomaly detection algorithms, they're in a separate GitHub repo, and they're all based on Spark and Scala. I'll be using Python and Notebook for only this kind of, like secondary activities, not the core anomaly algorithms, because they are all in Spark and Scala. Yeah, you can use sklearn, and you can try those two, isolation forest and local outlier factor. To get the maximum value for the next session, how can one prepare? So the next session is univariate Gaussian distribution. So I would focus on the next one is pretty much going to be basic statistics. So that's all there is for the next session. It's pure stats. How does one determine the contamination factor of LOA for isolation forest? Okay, I'll discuss those detailed questions when we come to the respective sessions. I'll skip them for now. Customized properties file, yeah. So the properties file are also in the repo, GitHub repo. If you want, I can show one right now. Let me see if I have one. Actually, those are properties file like in Java, like name equals value 1 per line. So that's same syntax. I know that typically it's not used in Python, but I actually invested a lot of time, implementing a nice configuration class on top of the base core, the Python library that came with it. So I use it in all my Python code. So let me see. Yeah, here is one. Can you see it? Yeah. Okay. Yeah, so that's it. So I think that was the last question. No, there is more. Customized one. Okay. Here's a customized one. Same name, same configuration name, but you may provide a different value. So in that case, it will override the default one. So internally, it's a so there is a configuration class I use. I can maybe try showing you. Let me see. I may have it open. No, not there. Let's see. Let's see if I have it open somewhere. Otherwise, anyway, that's not all that important. It's in my repo. I mean, you can look at it. It's called ML util. Oh, yeah. So this has this configuration class. I use something called a Python library called jprops, and then I built a wrapper Python class on top of that, providing a lot of useful, user-friendly methods for configuration management. So, for example, you can get the configuration as type data. You can define defaults in the configuration. You can make the configuration mandatory. For example, if it's not provided, it'll raise an exception. So I added all those features on top of the basic Python library. Okay, what else? Let's see, where was I? Okay, let's see. To get the maximum value from, okay, I think I went through that. Do we need to remove trend, do we need to remove seasonal trends? Removing it is one way, like I was saying, but you don't have to. I talked about two approaches. One is figure out what the seasonal cycle is with autocorrelation. And then once you have figured that out, let's say it's a daily cycle, then you take your historical data and build 24 models, one for each hour of the day. And then you can use the data as is. You don't have to remove anything. The other approach is to remove it and then run anomaly detection algorithm on the remainder, which is zero mean, Gaussian distribution. Yeah, I think that's the last question I see. Okay.
So yes, thank you everyone. Thank you, Pranav, for the session. We will follow up with the recording for the session, as well as we'll share the Google Doc for further information regarding the GitHub URL, and also we'll keep you updated about the next class and session.
Okay. Thank you everyone for attending. I see more questions. Okay. Oh, great course, sir. Thank you. All right.